Welcome back to another video in the Descriptive Statistics series. Numerical measures in statistics are quantitative values used to describe and summarize data. Key measures include measures of central tendency, measures of position, measures of dispersion, and measures of association. Together, these measures provide a comprehensive summary of the data's central behavior, spread, and relative positions, essential for understanding patterns and making comparisons. Now, let's have a deeper dive in numerical measures. Measures of central tendency, like the mean, average, median, middle value, and mode, most frequent value, which indicate where the data tends to cluster. Measures of position like percentiles and quartiles show the relative standing of data points within the dataset. Measures of variability assess data spread and include the range, difference between highest and lowest values, variance, average of squared differences from the mean, standard deviation, a measure of how spread out the values are around the mean, and coefficient of variation, a measure of relative variability. Measures of association between two variables, covariance and correlation coefficients, describe the strength and direction of a relationship between them, helping us understand if changes in one variable are related to changes in another. Together, these measures provide a comprehensive summary of the data's central behavior, spread, and relative positions, essential for understanding patterns and making comparisons. In statistics, numerical measures differ depending on whether they come from an entire population or just a sample. Population parameters. When we calculate a measure from the entire population, it's called a population parameter. These parameters give us a complete picture of the data and are often denoted by Greek letters. For example, the population mean is represented by the Greek letter mu, and the population standard deviation is denoted by sigma. Sample statistics. When we calculate a measure based on a sample, a subset of the population, it's called a sample statistic. These are estimates that help us infer information about the population. Sample statistics use Latin letters, such as x bar for the sample mean and s for the sample standard deviation. Using Greek letters for population parameters helps distinguish them from sample statistics, making it easier to identify whether a measure describes a full population or a sample. The mean is a fundamental way to measure the central location of a dataset, giving an average value that represents the data as a whole. It's calculated by summing all the values and dividing by the total count. As a simple arithmetic average, the mean provides a quick, easy-to-understand summary of the data center. However, it is also sensitive to outliers, extreme values that are much higher or lower than the rest, which can skew the mean and make it less representative of the dataset. For accurate use, it's important to note the distinction between sample mean and population mean. In a sample mean, you divide the sum of all sampled values by the sample size, while in a population mean, the entire population sum is divided by the total population size. For example, here, by adding all values in a sample and dividing by its size, 17, we get a sample mean of 11.41, providing a good indication of the sample's central tendency. The median is another key measure of central location that represents the middle value of a dataset, effectively splitting it so that half the observations fall below and half fall above this point. To find the median, first sort the data in ascending order. If the dataset has an odd number of observations, as shown in this example, the median is simply the middle value, which is 11. If the dataset has an even number of observations, the median is calculated as the average of the two middle values. Here it is the average of 10 and 11, which is 10.5. One advantage of the median over the mean is its resilience to outliers. Extreme values on either end of the data have little impact on the median, making it a more reliable measure of central tendency for skewed datasets. This property makes the median especially useful when data include unusually high or low values that could distort the mean. The mode is another measure of central location that identifies the most frequently occurring value in a dataset. It is particularly useful for qualitative data or categories, where values like colors or types are often repeated. The mode helps us understand what is most common or popular within a dataset. A dataset can have no mode if all values occur with the same frequency, the case of this example. A dataset can have no mode, one mode, unimodal, as the case is for this example, or multiple modes, multimodal, which shows that there are several values with the highest frequency. The mode can be less informative for quantitative data with many unique values. We can say that in this example, we only have one mode, which is 3, as it has the highest frequency. After removing one of the observations, we can see that we have 3 peaks. This means that now we are dealing with a multimodal datasets with modes 3, 12, and 16. Imagine you're meeting a new person named Jim, and you're trying to guess how many legs he has. You have a dataset on the leg counts of the world's population, which includes individuals with prosthetics or injuries. Given this dataset, which measure of central tendency, mean, median, or mode, would best help you predict how many legs Jim is likely to have. If you rely on the mean to find the central tendency, you would add up all the legs and divide by the total number of people. However, the mean is highly susceptible to outliers, meaning that a few individuals with fewer than 2 legs can skew this average. As a result, it should be surprising if you meet someone new, like Jim, and discover he has 2 legs. If you use the median, you would sort the values and locate the middle point. Given that most people have 2 legs, the median will also likely point to this typical value, suggesting that when meeting new people, you should generally expect to see someone with 2 legs. Finally, if you rely on the mode, you would determine the most frequently occurring number of legs in the dataset. Since the vast majority of the human population has 2 legs, the mode would indicate that you should expect Jim to have 2 legs. Now, considering all this, which statistic do you think will give you the most accurate prediction of how many legs Jim is likely to have? The pith percentile of a dataset is a specific value that indicates the point below which a given percentage p of the observations fall. In simpler terms, if you have a dataset and you want to know what the pith percentile is, this value will represent the point at which at least p% of the data is less than or equal to that value, and conversely, at least 100 minus p% of the data is greater than or equal to it. To calculate the pith percentile, you should follow these steps. Sort the data in ascending order. Calculate the index 1 where I is equal to p divided by 100 and multiplied by the size of the dataset, n. If is an integer, report the average values corresponding to the I and I plus 1 indexes in the sorted data. If is not an integer, report the value corresponding to the rounded up value of the calculated index I. In this example, we want to find the 10th percentile. We start by finding the index 1 by dividing 10 by 100 and multiplying it by sample size, which is 16. The index is equal to 1.6, which is not an integer. We rounded it up to 2. And report our 10th percentile as 3, which is value of the second observation in our sample. Quartiles are specific percentiles that divide a dataset into 4 equal parts, helping to summarize its distribution. The 0th percentile represents the smallest value in the dataset, while the 100th percentile corresponds to the largest value. The 25th percentile, known as the lower quartile, Q1, marks the point below which 25% of the observations fall. The 50th percentile is referred to as the median, Q2, indicating the middle value that separates the dataset into 2 equal halves, with 50% of the data below and 50% above it. Finally, the 75th percentile, called the upper quartile, Q3, signifies the value below which 75% of the data points lie. By identifying these quartiles, we can gain valuable insights into the spread and central tendency of the data, making it easier to analyze and interpret distributions. For example, to find Q1, first we need to find the index, I, which is equal to 25 divided by 100 multiplied by 16. The index is 4, which is an integer, and as a result, our lower quartile is the average of 4th and 5th values in our sorted data. Q1 is the average of 5 and 7, which is 6. It means 25% of our data is less than or equal to 6. Now, we will discuss range, interquartile range, variance, standard deviation, and coefficient of variation in this section. The range and interquartile range, IQR, are 2 important measures of variability that help describe the spread of data. The range is calculated by finding the difference between the largest and smallest values in a dataset, providing a simple overview of how far apart the extremes are. However, the range is highly sensitive to outliers, meaning that a single extreme value can significantly distort this measure. In contrast, the interquartile range focuses on the middle 50% of the data by calculating the difference between the upper quartile, Q3, and the lower quartile, Q1. This makes the IQR a more robust measure of variability, as it is not influenced by extreme values and thus offers a clearer picture of the data's central spread. Together, the range and IQR provide complementary insights into the variability of a dataset, helping to assess its overall distribution. In this example, the range equals 20-1 equals 19. Can you find the interquartile range? A box and whisker plot, also known as a box plot, is a graphical representation that summarizes the distribution of a dataset through its quartiles as well as lowest and highlights values alongside of its potential outliers. The plot consists of a rectangular box that spans from the lower quartile, Q1, to the upper quartile, Q3, with a vertical line inside the box indicating the median, Q2. The whiskers extend from the edges of the box to the smallest and largest values within a specified range, typically defined as 1.5 times the interquartile range, IQR, from Q1 and Q3. Any data points outside this range are considered outliers and are often plotted as individual dots. Box and whisker plots are useful for visualizing the central tendency, spread, and symmetry of data, making them an effective tool for comparing distributions across different groups or datasets. Here, we can see the box plots of the 3 iris species in the iris dataset. A more advanced version of box plots is the violin plot, which provides a comprehensive view of the distribution of numerical data. Unlike box plots that summarize data through a few statistics such as the median and quartiles, violin plots display the entire distribution of the dataset along with its probability density. This is achieved by showing a mirrored density plot on each side of the box plot, revealing the peaks and valleys in the data distribution. The wider sections of the violin indicate areas with a higher frequency of data points, while the narrower sections represent lower frequencies. Violin plots are particularly useful for visualizing complex data distributions, as they allow for a clear understanding of the data's shape, spread, and central tendency. This makes them an excellent tool for comparing multiple groups or categories, as they convey more information than traditional box plots, enabling analysts to identify patterns and insights within the data more effectively. Box plots are great for showing the quartiles of a dataset. It's possible to have multiple box plots that look identical, even though the underlying data distributions are significantly different. To address this, it's recommended to consider other visualization techniques. For instance, violin plots combine the simplicity of box plots with a density trace, showing the probability distribution of the data at different values. Variance and standard deviation are fundamental statistical measures used to quantify the spread or dispersion of a set of data points around their mean, average. Variance is defined as the average of the squared differences between each data point and the mean. It provides a measure of how much the data points deviate from the mean, with a higher variance indicating greater dispersion among the values. Standard deviation, on the other hand, is the square root of the variance and is expressed in the same units as the original data, making it easier to interpret. A lower standard deviation indicates that the data points tend to be closer to the mean, while a higher standard deviation suggests that the data points are spread out over a wider range of values. Together, variance and standard deviation provide valuable insights into the variability of data, helping analysts understand the degree of risk or uncertainty associated with a dataset. The coefficient of variation is a statistical measure of dispersion that expresses the extent of variability in relation to the mean of the dataset. It is calculated as the ratio of the standard deviation to the mean, often represented as a percentage. This measure is particularly useful because it allows for the comparison of variability across different datasets or variables, even when they have different units or scales. A higher coefficient of variation indicates greater dispersion relative to the mean, while a lower coefficient of variation suggests that the data points are closer to the mean. By using the coefficient of variation, researchers can assess the consistency or reliability of data. In this section, we cover the measures of association between two variables, namely covariance and correlation. When exploring the relationship between two variables, such as the effect of advertising expenditure on sales or the relationship between the length and width of iris petals, data is typically collected in pairs represented. As we saw, a scatter plot is commonly used to visually illustrate this paired data, allowing us to observe any patterns or relationship that may exist between the two variables. However, to quantify the strength and direction of this relationship, we can use statistical measures. Correlation and covariance are both statistical measures that help us understand the relationship between two variables, but they differ in their definitions, interpretations, and applications. Covariance measures the extent to which two variables change together. Specifically, it indicates whether an increase in one variable would correspond to an increase, positive covariance, or a decrease, negative covariance, in another variable. For instance, if we consider variables such as advertising expenditure and sales revenue, a positive covariance would suggest that as advertising increases, sales also tend to rise. However, covariance has some limitations. It can take any value from negative infinity to positive infinity, which makes it challenging to interpret. A covariance of 0 indicates no relationship, but the magnitude of covariance does not provide clear insights into the strength of the relationship. In contrast, correlation standardizes covariance by dividing it by the product of the standard deviations of the two variables. This results in a dimensionless measure that ranges from -1 to 1. A correlation coefficient of 1 indicates a perfect positive linear relationship, -1 signifies a perfect negative linear relationship, and 0 indicates no linear relationship at all. Because of its standardized nature, correlation is often easier to interpret than covariance. It not only informs us about the direction of the relationship, but also provides insight into its strength. For example, a correlation of 0.8 suggests a strong positive relationship between the variables, while a correlation of -0.5 indicates a moderate negative relationship. These are some examples of data with high, moderate, and lack of positive and negative correlations. Remember, a correlation coefficient of 0 means a lack of any meaningful correlation. So, your pairwise observations can be a horizontal line, which signifies the increase in x-axis variable has no impact on y-axis variable, as displayed in the plot G. Or it can be a display of random behavior, plot C, or patterns that cannot be explained, plot F. In plot F, the increase in x-axis variable is increasing the variable in y-axis, and after some point the increase in x-axis variable is decreasing the value of variable in y-axis. The phrase correlation does not imply causation underscores a fundamental principle in statistics. Just because two variables exhibit a statistical relationship does not mean that one variable directly causes changes in the other. For instance, if data shows a correlation between ice cream sales and drowning incidents, it would be misleading to conclude that buying ice cream leads to drowning. Instead, both variables may be influenced by a third factor, such as warm weather, which increases both ice cream consumption and swimming activity. Correlation can arise from various reasons, including coincidence, reverse causation, where the second variable influences the first, or the presence of confounding variables that affect both variables simultaneously. Thus, while correlation can provide valuable insights into relationships between variables, it is essential to conduct further investigation and analysis to establish causation and avoid drawing incorrect conclusions. Thank you for watching this video.